Okay. So let me share my screen. Okay. Okay. All right. So we'll be starting with what DoraHacks is and what Dōjō is. Um, okay. Okay. So what is Dōjō? Well, DoraHacks is an open source knowledge community focused on a cutting edge technology such as an encryption and also a Web3 and a code built by hackers. So DoraHacks regularly organizes knowledge sharing sections as in form of live broadcasts, audio and text. So the topics covered in the past are and they include both past and present. They include the L1 and L2 consensus algorithms. We have the architecture. We have related contents on GitHub repositories, and we have some of the specific topics covered also in that scrolls or Polygon ZK EVM. We have the Eigen hybrid proof systems. We have optimism, Aptos, Move language. We have cryptography as well, which of course includes the ZK proof, that's the zero knowledge proof. We have the public key encryption, hash functions, and also we have the lattice ciphers. So we'll be presenting on hash functions today. And I have many more, like the quantum computing. We also have satellite communications and spacecraft system designs, right? So before we start our presentation, I would like to talk a little more about DoraHacks because DoraHacks is a platform in which all these are being launched on. So I think let's take a quick peek at DoraHacks. So these are DoraHacks looks, and here we have ongoing bounties. Yeah, ongoing bounties. You can see research on 50 Aptos. So yeah, all the hackers out there, you can come in and if you're interested, you choose a research topic that you can write on, and then you present Evmos and many more. All right, this brings us to topic of today. Yeah, which is so I'll be presenting on Zcash SHA-256, and the outline of today's topic will be on fundamentals of the SHA-256. We'll also look at the practice of the SHA-256, and we'll look at pros and cons. Okay, so first, what is SHA-256? It is a cryptographic hash function that is widely used in various applications, such as digital signatures, encryption, authentication, and blockchain, of course. So the SHA-256 stands for Secure Hash Algorithm 256, which means it produces a fixed length of output of 256 bits. That's 30, that's 32 bytes from any input, regardless of its size or its content, be it like A, B, or C. It still gives you the same number of outputs, or even a string like a sentence. So the SHA-256 is a collision resistance, meaning that it is very unlikely that two different inputs will produce the same output. Just two different inputs is so unlikely that they will produce the same output. They probably will produce different outputs. So the SHA-256 was developed by the US National Security. We'll take a brief overview. That's the NSA, and published in 2001 as standard by the National Institute of Standards and Technology. That's the NIST. It is a part of the SHA-2 family of hash functions. It was actually taken out from the SHA-2 family, and it includes the SHA-224, the SHA-384, the SHA-512, the SHA-512 stroke 224. That's all 224. Then and we have the SHA 512 stroke 256, right? Okay, so we'll move to the next. So the SHA 256 can be implemented in various ways. So one of the ways it can be implemented are such as software, hardware, or it can be a combination of both. So one way of implementing the SHA 256 in hardware is to use a chip or an integrated circuit. That it contains all the necessary components like the logic to perform hash functions. So regarding the chip, like a chip can offer an advantage like such as speed, efficiency, security, and also portability, of course, because it's just really small in size and it's durable. But however, a chip has its limitations, such as cost, complexity, and compatibility. Not every system that is compatible with the chip also is relatively expensive. It's generally expensive. So it's not everyone that can afford it. So one example of the chip that implements the SHA-256 is the gadget interface chip, which we'll briefly look at. So a gadget interface chip is a device that connects a USB port and provides a simple interface for performing cryptographic operations. So basically, that's how it works. And this gadget interface can be used to generate uh, and also verify digital signatures. It can also be used to encrypt or decrypt the data. It can also be used to create or validate hashes. So the GI or the gadget interface chip can also be programmed to support like different hash functions such as the SHA-1, SHA-2, and SHA-3. Right? So we'll go to the next. So the GI it also consists of three main components. That's it consists of a microcontroller, a memory, and a cryptographic engine, of course, for it to solve the cryptographic problems or hashes. Then the microcontroller is the brain of the chip that controls the communication with the host computer and executes the instructions of the cryptographic operations. So now the memory is where the data and the keys are stored and accessed by the microcontroller. And the cryptographic engine now. The cryptographic engine is where the actual hash is performed. The cryptographic engine can either be dedicated hardware module or it can be a software module running on a microcontroller. Okay, we'll briefly look at a typical example, I think in a pictorial view. So the basic steps of performing the SHA-256 on a GI chip are as follows. One, the host computer has to send a command to the chip with data to be hashed and optionally a key. Could use a key. Secondly, the chip receives the command and it stores the data in the key in its memory. course, it's the memory that stores all this. We mentioned this earlier. Then three, chip invokes its cryptographic engine to compute the hash of the data using the SHA-256, optionally using a key. Then the chip itself returns the hash value to the host computer. Okay, here's a typical example of the flow, how it works. So from the steps above, is a pictorial view of what happens from your key back to the chip, from the chip then to your computer, and you see your hash when you send it back, maybe through your key to the chip. You can also get the result of your hash on the host computer. Basically, this is just a simple illustration of how it works. Um, okay, so SHA-256 has many advantages and disadvantages. So we'll briefly look at the advantages and the disadvantages. So what are the advantages? One, it provides strong security against brute force attacks. Yes. Two, it provides strong security against collision attacks as it will be an astronomical amount of time and resources to find two inputs that produce the same output. This could take a lot of time for the person trying to crack this, and he may eventually not even crack. So this is one of the advantages of using the SHA-256. Another advantage is it is widely adopted and supported by various standards, protocols, and platforms. So it has this universal acceptability where you're not learning something new, but yeah, you're working with something that is already accepted out there and it's easy to and it is relatively simple and efficient to implement in software or in hardware. So it goes both ways. Really, really helpful. Now we'll look at the disadvantages. So it has large output size compared to the other hash functions like the 1 and the 3. It really has a very large output size. We mentioned it has about 32 bytes of hash output size, which may increase the storage and the transmission cost, of course, not something we may want. The storage size and the transmission cost will definitely increase. So this is a disadvantage. Secondly, it's other hash. This one has been it's a known fact and future attacks or weaknesses that are yet to be discovered and disclosed. This is always a disadvantage when you are using. Okay, the last one, it may be subjected to legal and regulatory restrictions or requirements in some countries or regions. So this is something to take note. If you are building with the or using the SHA-256, are you working on, let it not be a region that it's being restricted or maybe the restrictions are just not worth it. All right. Next is practices of the SHA-256. So we look at the practices now. All right. So under the practices, we look at features. So firstly, we are going to look at cryptographic functions. So the image behind here is just an illustration of how cryptographic hash function works. This is the whole process. Here, the input message. Let's say the message is part the message with one followed by the other so that it can fit into the integer number of blocks. Then it passes down to see 502 bits. Then we have our block 1 and 2 all the way to our output hash value, which is 2 of hash value. Okay, let's check more illustrations. I think it will be more illustrations on the okay. Okay, let's go to the second point. Fixed output length. So the SHA-256 generates a hash value of 256, that's 32 bytes, as we mentioned earlier, in length. So this is something that is constant. It always produces this output, be it a number or a string, produces the same output. Then the third one is collision resistance. 256 exhibits high collision resistance, meaning it is statistically improbable for two different inputs to produce the same hash value, also mentioned earlier. And then the fourth one is the avalanche effect. This is a very important point to note. See, the smallest change in the input data leads to significant changes in the hash value. So it creates a dynamo effect throughout the output. So this avalanche effect ensures that every minor modification in the in the input, sorry, use vastly different hash values. So this is actually a very, 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 very strong feature of this SHA-256 that we should all know. That's why it's practically impossible to kind of match two figures with one to create the same um, hash output. So the next one is one-way function, which is the SHA-256 is designed to be a one-way function. So it makes it computationally infeasible to reverse the hashing process and to deduce the original input, just irreversible. Um, we also have the deterministic feature of the SHA-256, which, let's say, given the same inputs, the SHA-256 algorithm will always produce the same hash value, provided that the input is the same. But any change, like be it a full stop, a symbol, any kind of uh, point or any mark output. So the next one is the efficiency. How efficient is it? The SHA-256 strikes a balance between security and efficiency. It offers high level of security. This is a known fact. And being relatively fast is very fast in computing and making it suitable for a wide range of applications. It has that general, like, universal accessibility. So many systems are wide applicability. It's widely applicable. So many, like, okay, let's mention some of the places it's been applicable. You can see across various domains, includes digital signatures, it is in password storage, blockchain technology, and data integrity verification. So you see all these things. It has a wide applicability. It's applicable in so many different ways and different systems. And standard, standardization, which is another one of the feature, it's NIST approved standard. As we mentioned, of course, they worked on this, which is a big deal. Ensuring its implementation and security characteristics have undergone rigorous scrutiny and evaluation, right? Then the last one, its resistance to pre-image attacks. You should know this SHA-256 is a good option to go with. The SHA-2 algorithm resists pre-image attacks, making deducing an input corresponding to a specific hash value challenging. Very, very challenging when you try to use the pre-image attacks against the SHA-256. So then the next step is the application. The SHA-256 has proved its prowess in safeguarding various aspects of our digital lives. So let's explore the diverse applications. Okay. So one, the first application is protecting the data integrity. So the SHA-256 serves a vigilance guardian. It serves as a vigilant guardian of data integrity. It transforms data into a fixed size hash value, ensuring that even the slightest modifications in the input results in a vastly different output. We're getting to this later. Be it a string, as I mentioned earlier, or a symbol, it gives the same uh, number of hash outputs. And also, any changes made in maybe a string or a sentence, the overall hash changes. So this is one of uh, its data integrity. It protects the locations, verifying data signatures. So data signatures provide authenticity, to digital documents and communication. So the SHA-256 plays a vital role by creating a hash value of the content to be signed. So this hash value is then encrypted using a private key, forming the digital signature. Or let's say users can use the corresponding public key to decrypt and verify the signature from their own end, of course, ensuring the sender's identity and documents integrity. Okay, let's go to the next point. Next point is password hashing. So storing passwords in the raw form is risky, which we all know this, but the SHA-25 and salt, that's a random value, are employed to secure a hash password. So it's just like, let's say your password is let's say when you put it through a SHA-256 hash, everything changes into like an alphanumeric value. You have 0x blue, just random numbers created within the 256 bit. When hack through a password or get through, this is one of the strengths or use cases of the password hashing in SHA-256. Then we have verifying blockchain transactions. We can also be used to verify blockchain transactions. So how? That's what we're looking at. In blockchain, where transparency and security are paramount, we know in the aspect of transparency, we have our blockchain explorers, where we can always check our transactions and all the information embedded in it. SHA-256 stands as a cornerstone for this. It is used in proof of work mechanism to verify and link transactions into block. Alright, this um, basically uses this proof of work like the Bitcoin blockchain and I think formerly Ethereum when they were still using the proof of work to verify links transactions into the block. Hash contains the previous block hash and creating an immutable chain. It just works like it helps in validating. When a validator wants to validate a block, he has, let's say, five different transactions, or let's say 10. So the hash of the first transaction created should have should um, then the second one should show in the third one. In this way, they are all linked and no double spending is, and that way it can be validated. So this is a very important feature which ensures the consistency and the integrity of the entire blockchain. Bitcoin network uses this constantly. They are still using it. So we're going finally we are looking at pros and cons of the SHA-256. So we quickly dive into the pros. One, that's the security. The SHA-256 is considered highly secured during its resistance to collision attacks. I think we mentioned this earlier as well. So a collision occurs when two different inputs produce the same hash value, but from the features which we mentioned earlier, we discovered um, it's near impossible for you to produce two different uh, inputs that give you equal output. So this makes the security of the SHA-256 very strong. And while it's theoretically possible, it's computationally infeasible to find such collisions. Theoretically, it's possible. It has been proven, but about that, I personally I do not really believe you can have such. And here below is the diagram of have your input, you see your A, you could just go to B and just multiple strings with B to C. How would you guess this? And your output is bringing something entirely different. So this is just security is strong. So the second step is the speed. We have the SHA-256 is relatively fast in computation, very fast, making it efficient in many cryptographic applications such as digital signatures and also data integrity checks. So two, three, we have deterministic. It is very deterministic. So given it gives the same given same input, the SHA-256 will always produce the same output, ensuring consistency in cryptographic operation. As long as you give it the same input, it will always give you or produce the same uh, output. But once you change anything, it gives a different output entirely. So this is also a very good feature, something you can do. This is a pros. This is one of the pros things that you can do with SH256. Then the next point is it's widely adopted. The SHA256 is widely used and supported across various programming languages, libraries, and platforms, making it accessible for developers. And the next point is blockchain technology. It's used for in the blockchain technology. Example I mentioned was Bitcoin. Yeah, and the proof of work algorithm like the Bitcoin, I think Litecoin, and other blockchains that use this consensus algorithm. They usually adopt the SHA-256 because it's easily adoptable for the blockchain technology. For when you are using it for validating a block, it's very easy and it makes everything flow properly. And it easily identifies bad actors, those that are trying to like double spend. It's not possible to double spend with the 256, right? So finally, we are looking at cons of SHA 256. So one is no longer quantum safe. I think this is a new revelation. So with the advent of the quantum computing, the SHA 256 security is potentially at risk. We know what quantum computers can do. The quantum computers should potentially break the SHA 256 through the Grover's algorithm, which would make it less secure in a post-quantum world. Maybe when we get to the world where everything is quantum, like computers solve the most complex problems in seconds because of yeah. So below is the way it's being computed, right? So this one way definitely quantum computers can break SHA-256. An example, yeah, typically. So when you have your k, which is a constant, you have 0 to 63. So these are hash values, or rather output values produced. This zero, it produces a different hash value. You can see one, it produces. So each one of these are different outputs that are produced by the SHA-256. They are all different and unique. Anything change, one is different from two, two is different from three. All have the same length, but actually different figures, different values in the output. Um, okay, deterministic. We're going to use deterministic again. So while determinism is a pro for security, which we already established, it can also be a con for privacy. So given the same input, SHA-256 will always produce the same hash, which can potentially leak information about the inputs of the data. So it's just like here from example like one, when you input a one in the SHA-256, it's always going to give you this value, this 0x71374491. So everyone would know, yes, this is a set giving output. It's always going to give us the same output any day, anytime. As long as you do not change the one, one will always remain one. This output will always remain this output. So this is actually a great concern in terms of privacy, because everyone would actually know, yeah, this is what this is. Okay. So for the third one, is not suitable for password storage. The SHA-256 is not suitable for security storing passwords. It lacks the necessary features like salting and stretching, which is essential for password security. That is just it. You want to maybe, yeah, you want to create like a large string, maybe string, and maybe you have float, you have different decimals in your password. The hash function will still give you the same length of output. So this is really not suitable for password storage at all. Not really. Um, okay, so we go to the next step. That's resource intensive. It's resource intensive. So while it's fast, the SHA-256 can still be resource intensive for large scale applications or devices with limited computational power. So while it's doing this, if from earlier as we mentioned the steps, like when you have the chip, when you want to use like a chip to maybe integrate with, let's say, blockchain technology, the chip itself is expensive to get. That aside, storing the data, the memory is also expensive because it stores like it gives relatively large output. So this definitely takes a toll on the memory. You spend much, is not a secret, and it's definitely resource intensive. That's just the point. Okay. Then the last point we take is the size of the hash volume. So the SHA-256 produces a fixed size output for 256 bits, which can be larger than necessary for some applications, leading to wasted storage space. So I just mentioned this now. So let me go back to this image. You can see this all the outputs just the same number. One, two, three, four, five. So it gives you that same 256 8 bit. This, by the way, this is just an example. So it will always give you the same length of output, which is always 256 bits, where it got its name from. So it's not going to be suitable for some of the applications, right? And this could lead to wastage. Maybe you just need maybe a full stop, one, two, or it's just storing these random strings. and numbers, right? So this will definitely lead to storage wastage, memory wastage, more resources. You spend more, and yeah. And here are the references where I got some of the materials from. Right. I hope this was a nice workshop. I hope you learned something today. Thank you very much. I will entertain questions if there are any. If there are any questions, okay, Lynn. Um, okay, I think this will bring us to the end of the workshop on Zcash SHA-256. Thank you for coming once again.